Alright, welcome back. Today we're going to jump back to our single cycle processor because I know everyone out there totally nailed this thing last night, got it in there, every instruction working flawlessly, and it is time to proceed to the next processor. So that's what we're going to do. First off, we're going to do a quick look at the single cycle processor, then I'm going to go over the next evolution of the single cycle processor. Spoiler alert, it's called the multi-cycle processor. I'm sure none of y'all saw that coming. But we are not going to actually implement the multi-cycle processor in Verilog. We're going to skip that one and then proceed to the next one, which I wish I could leave as a surprise, but unfortunately we're all online, so there's not much I can do about that. And we'll get to our final processor for this course after today's lecture. So let's go ahead and jump back to the single cycle processor. If you noticed in here, we looked at the single cycle processor and we're trying to figure out what the longest path was, so aka what is going to be the cycle time. Well, it's based on a gate delay, and in this situation it's about 85 gates deep. If we say 20 gates for the instruction memory, it takes another 5 to go through the register file, 225s, well it could be 30 in order to go through the sign extend and into this multiplexer, which could be 30. Because the multiplexer adds some to 25. The ALU, if we're using a carry look ahead adder and not the ripple carry adder, maybe gets to 54. And then 54, if afterwards you have to use that in order to do a memory lookup, then it goes to 20. So about 74, cycle that all back around to here. Add some more cycles for the mux, and then if it has to write it, it's another 5 gates. So we're saying about 85 gates just to give us a number. Now you can go through here and you can look at all the other different components happening. Most of them, or a lot of them, are in parallel. For example, it does take 28 cycles before the control ROM can give out, 28 gate delays before the control ROM can give the proper inputs to each of these muxes. So there is some delay there. But if we calculate it out, we said that this is about 85 gate delays. Now, the problem here is all instructions run at the speed of the lowest instruction. Alright, we haven't gotten into further instructions yet. We will momentarily, but before we do that, it's important to note that adding a long instruction can hurt performance. Because if you want to do multiply, we haven't talked about how to do multiply yet, but hopefully you can see that if you wish to multiply something, you're really just adding multiple times. Well, if you're adding a lot, then that's going to be a lot longer than just a simple addition. So if we added a multiply, what would happen with our single cycle processor? Well, the cycle count would drop to the cycle or the gate delay of a multiply, and that would be for all instructions, which would definitely slow down our processor overall. Another problem is we can't reuse any part of the processor. If you notice that we are doing an addition here, we're doing an addition here, and we're doing an addition here. That's 3 adders. We really only need 1 adder if you think about it, because can't we just use the same adder to do all these additions? On this design, we have to have 3 of them. It would be nice if we could reuse them. That would save us some space, which of course in the end would save us time and money, area, and of course energy. Also, there's no profit in making the common case fast, because since every instruction runs at the slowest, this becomes a big issue. This is particularly important for loads. We went ahead and went through loads in this class, or this session of the class, due to how everything laid out. And so you can tell that this 20 gate delays may end up being 300 gate delays, or 300 clock cycles before anything can come back. Or it could be 20. It's variable. So that means that a load is significantly longer than an add. So it comes to be that even if you're trying to you want to add more instructions, or even if you wanted to make addition faster, it wouldn't help you out because everything has to run at the speed of the slowest thing, which are loads. So let's go take another quick look at this. So let's look at these 4 instructions right here. I've realized this says store word, and that should be move S, and this is load word, which should be move L. So add, then getting the instruction, they all take 2 nanoseconds. They say for sake of argument, reading the register is another. The ALU operation is 2. Memory will say is 2 nanoseconds, which is not the case. It's more like 20, but let's go stick with 2 for now. And then we'll just say writing a register is another 1 nanosecond. Now, add doesn't have to go to mem, it has to do everything else, so that's 6 nanoseconds. Branch if equal, aka branch or jump, that's the JA instruction. In fact, let me go ahead and fix this now for everyone at home, because I just didn't get to it. There we go. A little offset. But the idea here now is that this is a little more accurate. But point is, each of these instructions are going to take a different amount of time in order to complete. So that means that the add instruction, even though it should only take 6 nanoseconds, is going to take 8 nanoseconds because our clock cycle is based upon the based upon the slowest instruction, which is our move L, or aka our load word. So what does that mean? Well, we're assuming 100 instructions executed, 25% are loads, 10% are stores, 45% are adds, and 20% are the branches, aka the CMP and the JA. The cycle time on a single cycle is 100 times 8 because everything has to run at the slowest speed, which is 800 nanoseconds. But optimal execution in this regard would be 640 nanoseconds. That's a pretty significant drop, especially if you're thinking about a program that's going to take weeks. You know, if it normally takes 5 weeks, that drops it down to probably just under 4 weeks. Pretty big boost. And of course, this number even becomes larger when you take in the fact that the loads actually take way longer than just 8 nanoseconds. So the idea here is, instead of having every single instruction take one whole cycle, we're going to have a multi-cycle execution where every instruction takes multiple cycles in order to complete. And we're going to divide up what each cycle is doing based on the instruction. So cycle time is greatly reduced because we're going to break up every instruction into multiple cycles. Slower instructions take more cycles, but faster instructions take fewer cycles. That way we can hopefully leverage the fact that add takes fewer cycles. And we can reuse data path elements for a smaller circuit, which would be great. Since you are reusing elements for purposes, you need to add more or wider muxes for decision. We may have to have extra registers, and the control may be more complicated. So let's go ahead and take a look about what this would look like. Right here we're looking at our single cycle architecture that we looked at beforehand. We're going to go and get rid of these adders because we're going to reuse the adder and the ALU to do everything. Get rid of data memory. And so cycle 1 is just going to be fetching the instructions. Cycle 2 might be the register file, and cycle 3 might be working with the ALU. And there might be a couple of extra cycles that we're not showing here. But notice that now one instruction is chopped up into 3. Now you may think, well, won't that take longer? That is a good observation in one regard, but if you look at it, if we're chopping up the instructions into thirds, that means we can triple our clock time, which means we're going to have basically a wash. But since some instructions will take fewer cycles, those will go faster. So it may look something more like this. And you may have to, program counter, memory. Notice that this will be for both instruction and data. Instruction register, which is going to hold the register for the instruction, and then that'll go ahead and forward to the ALU if it needs to read to it, and then forward to the the muxes to the ALU for any result, and of course that result may go back to the program counter or back to the mux for memory if you need to do a load word, or it may go back to the register file in order to write to it, and there of course our sign extender. Notice now I have the control as a red circle. That's because our control logic in this regard is going to be way more complicated. But in addition to controlling these inputs to each one, it's got to also control, are we writing to the program counter? What's the mux for the adder to the instruction memory? Are we enable reading and writing? Are we reading and writing? Are we enable the overriding of the register? Of course, we'll have to overwrite this when we read a new instruction. To the mux, which one are we taking from, which part of the instruction register are we taking? And this mux, are we forwarding straight from instruction, or from, the memory? Okay, are we going to write the data for a load word, or are we going to write the output from an ALU? Of course, we need to enable the register file for writing, and then we also need to know in these two ALUs which inputs are we selecting. Notice that the 1 is for the PC plus 1, and then 0 is, of course, if you're just adding 0, aka a base of 0. And then the ALU, which operation you're doing. So this is definitely more complicated when it comes to the control logic, but hopefully you can see that we've eliminated a couple of components, namely the adder. And if you recall, our adders were pretty big compared to everything else. So for this design, the multi-cycle is advantageous. So the state machine may look something like this. Notice that each instruction starts at 0 where it fetches. Then state 1 would be a decode, and then after it's been decoded will be the number of instructions that may have to occur. So you may need to have add, which would be 2, NAND or AND, which would be another 2, load word or move L, which would be 3, and then store words would be right here, followed by the jump instruction here. I'm going to pause for a moment because I need to sit down and